Hello friends, I am Snehal and I am teaching you physics. In last lecture we discussed some experimental observations about static electricity and the Coulomb's law. So let us start by recalling Coulomb's law. Suppose we have two charges Q1 and Q2 and R be the distance between two charges. Then the force of attraction or repulsion, the electrostatic force, between these two charges is given by Coulomb's law, and the force is 1 over 4 pi epsilon naught into Q1 Q2 divided by R squared. Epsilon naught is a constant which we call permittivity of free space. Now let us write this constant as K equals to 1 over 4 pi epsilon naught, and its value is 9 multiplied by 10 raised to 9 Newton meter squared per Coulomb squared. So this is the Coulomb's law. Now let us compare this force, the Coulomb's force or the electrostatic force, with the force of gravity to find out its strength. So suppose we have two electrons. Now charge on electron is E, which is minus of 1.6 into 10 raised to minus 19 coulombs. So actually E is positive number, so this is minus of E. Okay, and mass of electrons Me is equal to 9.1 multiplied by 10 raised to minus 31 kgs. Now the electrostatic force between electrons, let us denote it by Fe, and its magnitude will be equal to this K multiplied by charge on first electron into charge on second electron divided by R squared. So it is E times E, or E squared over R squared. And the gravitational force is given by Newton's law of gravity, and we know that Newton's law of gravity is the gravitational force is G into m1 times m2 divided by R squared. Here m1 is equal to m2 and it is me. So I can write me squared upon R squared. This is gravitational force between the two electrons. Let us put this suffix G here, and let's take magnitude only. So the magnitude of the electrostatic force divided by magnitude of gravitational force is equal to K into E squared upon R squared, and dividing by this term is same as multiplying by its reciprocal. So let's multiply by its reciprocal. So it is R squared upon G me squared. Now this R squared and R squared gets cancelled, and what we are left with is K E squared upon G me squared. So let me write it here, and let us substitute the values. So the electrostatic force, magnitude of electrostatic force divided by magnitude of gravitational force is equal to K times E squared upon G into ME squared. Now let us substitute all the values. So we know that K is 9 into 10 raised to 9 and E is charge on electron, so it is 1.6 into 10 raised to minus 19. So this is 1.6 multiplied by 10 raised to minus 19 and there is square of that. G is 6.7 into 10 raised to minus 11. This is the universal gravitational constant. Its value is 6.7 into 10 raised to minus 11. And mass of electron is 9.1 into 10 raised to minus 31. And there is square of that too. Okay. Now we are not interested in the exact number, but only the order of magnitude. So whatever number is there which is greater than 5, we will make it 10, approximately 10, because we are interested in order of magnitude only, and whatever numbers are there which are less than 5, we will make it equal to 1. So this is, its order of magnitude is 10 for this 9 into 10 raised to 9 multiplied by, let's make this 1, so 1 square, 10 raised to minus 19, square of that, so it is 10 raised to minus 38, divided by, let's make this 6.7 equal to 10 multiplied by 10 raised to minus 11 multiplied by 9.1 will make it 10, so 10 squared to 10 raised to minus 62. Okay, now this thing gets cancelled and let's take the other things in numerator, and then if we do all these calculations we'll get 10 raised to 42. So this is the magnitude of electrostatic force divided by magnitude of gravitational force. So it is roughly of the order of 10 raised to 42. That is, the electrostatic force is stronger by gravitational force by this much amount. It is 10 raised to 42 times stronger than gravity. So let me write force of electrostatics or the electromagnetic force is 10 raised to 42 times stronger than gravity. Now suppose we have more than two charges. So suppose this is Q1, Q2, then Q3, Q4 and so on up to Qn. Then what will be total force on this Q1 due to all other charges? So we know that force is a vector quantity. So total force on Q1 is definitely not equal to the sum of magnitudes due to all other charges. It is vector sum of the forces, the individual forces exerted by these other charges. So this theorem or this principle is called as principle of superposition of forces. Let us see that now. So this is a vector directed from Q2 to Q1. This is R21 bar. The vector directed from Q3 to Q1 is R31 bar. And similarly from Q4 to Q1 it is R41 bar. And so on. Now force on Q1 due to Q2 is F12. This is force on 1 due to 2. It is equal to 1 over 4 pi epsilon naught into Q1 Q2 divided by R12 squared. R12 is the distance multiplied. This is the magnitude. So to show the direction, we use this unit vector, and forces from Q2 acting on Q1. So the unit vector is R21 directed from Q2 to Q1. So it is R21 cap. Force on Q1 due Q3 F13 is equal to 1 over 4 pi epsilon naught into Q1 Q3 or R13 squared, and now the unit vector will be directed from Q3 to Q1, so it is R31 cap, and so on up to the Qn. Then principle of superposition, it says that total force on Q1 equals to the vector sum and this word is important, it is vector sum of all individual forces acting on Q1. So the total force on Q1, let's write it as F1. F1 is the total force on Q1. So it is equal to force on 1 due to Q2 plus F13. So force on Q1 due to Q3 plus force on 1 due to Q4 plus so on up to plus force on 1 due to the NH charge. Okay. Now let us write formulae for all those forces. So I can write F1 bar is equal to 1 over 4 pi epsilon naught multiplied by Q1 Q2 upon R12 squared into R21 cap. This is for F12 bar, plus for F13 bar we have 1 over 4 pi epsilon naught into Q1 times Q3 divided by R13 squared into R31 cap, and plus so on up to plus. Let's write it for NH charge. So force due to NH charge will be 4 pi epsilon naught into Q1 times Qn divided by R1n squared multiplied by Rn1 cap. Now let's take this 1 over 4 pi epsilon naught times Q1 common from all the terms. So let me write F1 bar equals to 1 over 4 pi epsilon naught into Q1 times Q2 upon R12 squared into R21 cap, plus from this term we have Q3 over R13 squared multiplied by R31 cap, plus so on up to plus Qn upon R1n squared into Rn1 cap. So this is the total force, and we can use summation sign to write down these terms inside the bracket. So this is equal to 1 over 4 pi epsilon naught multiplied by Q1 summation sign. Let's take some I equals to 2 to n. I am taking from this index. So this is equal to qi divided by r1i squared multiplied by r I1 cap. So this is force on 1 due to all the other charges. Now the things will get clear if we take an example. So far this is just a notation, but let us remember this: the total force on Q1 is the vector sum, not scalar sum. It's the vector sum of all individual forces acting on Q1. Let's take an example. Now suppose we have three charges kept on three corners of an equilateral triangle. So this is Q1 equals to -1 Coulomb. Let's take Q2 equals to 1 Coulomb and Q3 equals to 1 Coulomb respectively. And let's take side of this triangle to be equal to 3 meters for simplicity. So this side L, or let's call it R, equals to 3 meters. Now we are interested in finding out the total force on this Q1 due to the Q2 and Q3. Okay, so the superposition principle tells us that total force F1 bar will be equal to F12 bar plus F13 bar. So total force on Q1 F1 bar equals to F12 bar, force due to Q2, plus F13 bar, which is force due to Q3. Now this charge is negative and these charges are positive. So force is going to be attractive. So Q2 will pull Q1 towards it. So force due to Q2 will be directed along this line. And force due to Q3 will be directed like this, along this line. And their magnitudes will be same, because magnitudes of these charges are same, and the distance between them, which is length of side of equilateral triangle, it is also same. So magnitude of forces F12 bar and F13 bar is going to be same. So let me write it here. F12 bar's magnitude equals to magnitude of F13 bar, and let's take it equal to some F. Okay, now let us resolve F12 and F13 in rectangular components in order to add them. So this angle is 60 degrees because this is equilateral triangle. Let me draw this vertical and horizontal lines. Now suppose this angle is theta, so this angle will also be equal to theta. Let us resolve the forces. So for F12, this component will be F12 sine theta, and this component will be F12 cosine theta. So we can remember it this way: through the angle cosine component, cos component, and away from the angle sine component. So this component will be F12 cosine theta. Similarly for F13 also this angle is theta, so we will have component in this direction. So let me write total force in this direction to be equal to F12 cosine theta plus F13 cosine theta. Okay, and the away from angle, this component will be equal to F12 sine theta. This is Q1 equals to -1 Coulomb. Okay, and for F13, the away from angle component, which is this component, this much, is equal to F13 sine theta. Okay, now finding the net force is very simple. As you can see that the magnitude of F12 is equal to magnitude of F13, which is F, and these components F12 sine theta and F13 sine theta, they have equal magnitude but opposite direction, so they get cancelled out, and total force is just in this downward direction. So total force is F1, magnitude of F1 will be equal to magnitude of these two, F12 cosine theta plus F13 cosine theta. Okay, which is equal to, because F12 and F13 is equal to F, so this will be equal to F cosine theta plus F cosine theta, which is 2F cosine theta, which is net force. Okay, so let's find out F. So F will be equal to K into Q1, Q2. We are taking just magnitude, so magnitude of this divided by R squared. And we know that K is equal to 9 multiplied by 10 raised to 9. Q1 and Q2 have magnitude equal to 1. So this is -1 into 1, and we are taking mod of that. So which is equal to 1 divided by R square, and we have taken R equals to 3 meters. So this is going to be 3 square, which is 9. So this 3 square and 9 gets cancelled. So we have F equals to 10 raised to 9 newtons. So the total force, which is F1, F1 equals to 2F cosine theta, and theta is 30 degrees, so it is 2 times of 10 raised to 9 multiplied by cosine of 30 degrees, and I believe that cosine of 30 is square root of 3 by 2. So this 2 and 2 gets cancelled, and we have the total force F1 equals to root 3 multiplied by 10 raised to 9 newtons. Okay, so this is how we find total force on any charge due to the combination of maybe n number of charges. So procedure will be same. We will find out all the individual forces, then we will resolve the components, all those forces in the rectangular components, and then we'll add the respective components to find out the net force. Now let us define an important quantity, and we call that quantity the electric field. So suppose we have this charge capital Q placed somewhere in space, and we bring in some other charge, let's call it small q, and we keep it at distance r away from capital Q. So we know that the moment we bring in this charge small q, it experiences some force due to the capital Q, and the force is given by 1 over 4 pi epsilon naught into magnitude of first charge multiplied by magnitude of second charge divided by square of the distance between two charges. Now question is, where did this force come from, or what was there at this point before we brought in this small q. So the answer to these questions is, the moment we put this capital Q at this point, it created its effect in surrounding region at each and every point of its surrounding, and we call that effect the electric field of this charge. So we can write this force in this form: F equals to this term 1 over 4 pi epsilon naught into Q over R square multiplied by this other charge, small q. And we call this term the electric field of this charge. So this is E of this q. So we can write this force which is acting on this charge kept at this point, it is equal to the electric field created by other charges. In this case, there is only one charge, but it is equal to the electric field created by other charges multiplied by the magnitude of this charge. So F is equal to electric field at that point multiplied by the charge we keep. Okay. So the electric field is equal to 1 over 4 pi epsilon naught multiplied by Q over R squared. Now, as you can see, this electric field is independent of the second charge, as it should be, because it is the electric field of this charge, capital Q, and it depends on this charge. So this is the magnitude of electric field. Now F is equal to E times Q. So E is equal to F divided by Q. The charge whose electric field we are finding out is called as source charge. So this capital Q is called as source charge, and the charge on which we found the force to calculate electric field, this one is called as the test charge. Conventionally, we take this test charge to be positive. So this small q is always going to be positive, and electric field is a vector quantity because on right hand side we have this force F divided by Q. Q is scalar, F is vector, so electric field has to be a vector. So the direction of E bar will be along direction of the force experienced by this charge. So it is F bar divided by Q. So let me write a formal definition of electric field. It is equal to limit this test charge tends to 0, force experienced by test charge divided by magnitude of test charge. This is the formal way of writing electric field. And why is that? It's because the test charge should be so small, it should be negligibly small, because if test charge is large, then it will disturb this charge also, and we don't want that. We want to measure acceleration of this charge only, so only this charge should get accelerated and not this one. Okay, so that's why we take this limit q tends to 0. Okay, now we have defined the electric field or effect of the source charge, and we know that it's a vector quantity. So can we draw this quantity pictorially, or can we represent it? We know that vectors are represented by arrows in space, Now suppose we have charge of Q equals to plus 1 Coulomb. Then we draw these radially outwards continuous lines to represent its electric field. And why do we draw these lines radially outwards? It's because if we keep any test charge somewhere in the surrounding of this charge, then it will be repelled and it will be pushed away radially outwards. So force is radially outwards, electric field will be radially outwards. Now it should be clear that if we draw 4 lines for charge of 1 Coulomb, then we will have to draw 8 lines for charge of 2 Coulomb, 12 lines for charge of 3 Coulomb, and so on. So this is for positive charge. Suppose we have negative charge Q equals to minus 1 Coulomb, then we again draw 4 lines because we drew 4 lines for positive 1 Coulomb of charge. But the difference here will be these lines will have these arrows pointed radially inwards, because the test charge put somewhere surrounding this charge will be pulled radially inwards. So because these lines shows direction of electric field, we call these lines electric field lines. Now direction is okay, but have we lost an information about magnitude of electric field? So answer is no, but we have to define electric field carefully in order to have information about magnitude contained in these electric field lines. So we define electric field like this. So electric field is defined as number of electric field lines passing normally or perpendicular per unit area. Okay, so let us try to understand this definition of electric field. So suppose we have any positive source charge, and these are the electric field lines for that charge. Okay, so this is charge Q. Now we are defining electric field E equals to number of field lines passing per unit perpendicular area. Now suppose we go distance r away from the charge and collect all the points distance r away from the charge, then join all those points, then locus of all such points will give us a sphere. So let us draw a sphere at some distance. Suppose this is distance r, and as you can see, the surface of that sphere is perpendicular to the electric field lines. So we can define electric field as number of field lines passing per unit spherical area. So divided by, I can say, area of a sphere. So it is number of field lines divided by 4 pi r square, because area of a sphere is 4 pi r square. So this is for electric field. Now let's draw another sphere at distance 2r away from the charge. sorry. So it will be something like this. So this distance, this much distance is 2r. Now electric field at distance r away will be number of field lines divided by 4 pi r square. For distance 2r, the distance is increased to twice. So the electric field now will be the number of field lines divided by 4 pi, and instead of r we will have 2r square, that is 4r square. So as you can see, the electric field at distance 2r is 1/4 of the electric field at distance r, as it should be, as it is clear from this equation. E equals to 1 over 4 pi epsilon naught multiplied by q over r square. So in this way, the information about magnitude of electric field is also contained in electric field lines. So the intensity or the magnitude of electric field is high in the region where electric field lines are close to each other. As we go away from the charge, electric field lines get separated from each other. So the electric field decreases there. Okay, and then now we can settle this issue of drawing the number of electric field lines once and for all if we just equate these two equations. So equation 1 and 2. So if we just equate them, then we'll get the number of field lines we have to draw will be equal to q divided by epsilon naught. And number of field lines passing normally through an area, it is called as flux. So number of field lines, we call it flux or the electric flux, because these are electric field lines. And now we have reached to a statement of a popular law of electrostatic by Gauss. It is called as Gauss's law, but we have reached to this statement quite informally. Anyways, so number of electric field lines we have to draw. If we want to draw it rigorously, then it will be q divided by epsilon naught. But it doesn't matter because this is just for the sake of representation. Okay, so this is about electric field lines. Now let us see some properties of electric field lines to conclude this session. And properties are: electric field lines start at positive charge and end at negative charge. The second property is that they are dense in region of strong electric field and separated in region of weak electric field. So electric field lines start at positive charge and they are radially outwards from positive charge and end at the negative charge. Okay, so for negative charge, electric field lines are radially inwards. Second property is they are dense in the region of strong electric field, as we seen just now, and they are separated. So they are separated apart in the region of weak electric field. Okay. Then property number 3 is electric field lines cannot cross each other. Cannot cross each other. Then the fourth property is they do not form, they cannot form closed loops. Okay. So third property says that electric field lines cannot cross each other. So now we should think why electric field lines cannot cross each other. And answer is because suppose they cross each other. So this is one electric field line, this is another electric field line, and we know that the tangent to the electric field shows the direction of, tangent to the electric field line shows the direction of electric field at any point. So at this point we have two tangents. Okay, that is another property. Actually, I should have written it here at the top. So tangent to electric field line at any point represents direction of electric field at that point. It's because the direction of electric field line and direction of the tangent at any point, it will be identical. Okay, so now this is electric field line number 1, this is second electric field line, and as you can see at this point, this line, this electric field line is going in this direction, this electric field line is going in some other direction. So what will be the direction of any electric field at that point? Okay, so now we cannot have this case of crossing of electric field lines because the direction of electric field at any point will be fixed. It will be only one direction and not two directions like this. Okay, anyways, these are the properties of electric field lines. Now we have seen a lot of things in this lecture. Now you should revise all these things and you should definitely try some problems on the Coulomb's law and the superposition principle. In next lecture, we'll find out the electric field due to two or more charges. Thanks for watching the lecture.